Hello everyone, Nathan Zimmerman here, and in front of you is a picture of the ST Discovery board, which is probably one of the cheapest microcontroller development boards on the market, and it is also incredibly powerful. Previously, I used the MSP430 Launchpad. However, overnight they decided to more than double the price on it, so I've been looking for other options. Then I discovered this guy, which is probably one of the cheapest on the market, and it is also incredibly powerful. So what this video will be is it'll be a brief introduction to how to set up the integrated development environment, as well as how to write a simple blinky LED program. So the first thing that you're going to do is you're obviously going to have to purchase the development environment. You can purchase it on a manufacturer's page or distributors such as DigiKey. They have a couple different variants per processor. I'm going to go with the cheapest, which is currently $8, and the processor on there is a Cortex M0 32-bit instruction set processor. It has a max clock speed of 48 megahertz. It has 55 GPIOs. It has a lot of basic serial hardware IOs such as SPI, I2C, and UART. It has some other features such as direct memory access. It has a 12-bit ADC. It has 64 kilobytes of flash, and it has 8 kilobytes of RAM. So it's a pretty powerful processor, and then some people complain about the fact that it's surface mount. However, as soon as you start getting familiar with surface mount packages, the better. And as soon as you get familiar with like building your own reflow oven as a hobbyist, the better, because that really empowers you and enables you to use very nice processors such as this Cortex M0, and it also helps reduce the cost of your overall projects because you're able to use processors like this, and they only cost, say, $3.77. And you're not forced to try to incorporate a very expensive development board into your project, or to buy some large dip processor or through-hole processor that isn't very powerful. So I'm a huge fan of these. And I'm a huge fan of the board in general, except for one point, that is that it doesn't have its own free integrated development environment. They tell you to explore commercial options, and the problem with that is the commercial options, of course, have something like a code size limit. This has 64 kilobytes of flash. However, most IDEs that are free out there limit you to 32. And then they make you pay probably thousands of dollars in order to get the full version. And I'm a hobbyist, and I'm buying this to, I don't know, run little, small, low quantity hobbyist projects, and I'm not really in the mood to spend a whole lot of money on an integrated development environment. So I do the next best thing, which is check out the open source options. And thankfully, in the case of this development board, there's a really nice open source option out there that a friend made me aware of called, I'm going to murder the enunciation of this, but I believe it's called Kukox, maybe. Anyhow, it's a free open source integrated development environment with absolutely no code limit. And even better yet, it works with the built-in programmer on this development board. So in order to use this, go to the co-IDE page, scroll down. They got some information about the download. They note that the GCC toolchain is not integrated into the development environment, so you're going to have to download it first. Click this link, and that should take you to some GNU page. And on here, provided you're using Windows, all it is it's just an executable. You run it, and you're done. So make sure you do that first, and then go back to the download page. And I'd recommend downloading this this Co-Center. I believe it's like a download manager that you can use to simplify the process. So once you download that and you open it up, it'll look something like this. And so what you want to do is you want to download the co-IDE and install it. You'll want to download the Cocox CoFlash utility for programming. You're going to want to install that as well. And then as far as opening goes, you're going to want to open this this Flash utility first, run it, and then our board, this segment of the board uses a processor to emulate a JTAG debugger and programmer. So when we go back to our Flash utility, we're going to want to change this from whatever it's default set to the ST link, which is what this segment of our board is here. It acts as an ST link. So you're going to want to click that, I guess hit close, and then you're going to want to go back to your center, run the integrated development environment. And then if you have any experience with IDEs in the past, this should hopefully look familiar. It looks like some Eclipse-based development environment. First thing you're going to want to do once you open it up is you're going to want to configure it to use your GCC toolchain. So go to Project, select Toolchain Path, go to Browse, and then you're going to want to browse to the location on your computer. In my case, it's under Program Files x86 because I'm on 64-bit Windows 7, and then go to your GNU Tools ARM Embedded, go to your version number, and then go to Binary and click OK and OK. And the toolchain should be all set to go, and hopefully the programmer is all set to go. One thing that I just remembered, which is of crucial importance in order to get the programmer to work, you're going to probably want to do this before you even open up this IDE, is you got to install the Windows drivers for the ST link. You got to install the Windows drivers for this segment of your board. So I'd recommend doing this even before you plug your board in. Go to this ST page, and I'll provide the link in my YouTube video. But anyhow, it's called ST Link version 2 USB drivers for Windows 7, Vista, and XP. Download this, and it's just an executable. Hit run, and you should be good to go. So going back to the IDE, the first thing we're going to want to do for our blinking LED project is, of course, to create the project. So click Project, go to New Project, give it a name, Blinking LEDs 2. I was having some issues at the start, so that's why I have the 2 there at the end, because I've made a few blinking LED projects already. Hit Next, and you'll come to this model page, and they don't have one for the Discovery board, so we're going to have to use the chip that's on our board. So hit Next. Our processor is made by ST. It's a Cortex M0, and I believe it's the last one on this list. To verify that, you can go to ST's website and download the schematic for the development board. And as you can see, it's just a standard Altium schematic. The first page is kind of your board overview. The second page here, I believe, is the programmer. And I believe this ARM core here, I think that's a Cortex M3. They're repurposing this to act as a programmer, and you can see some associated circuitry with that. And then here is the ARM processor that we're actually evaluating. This F0, which I believe means Cortex M0. And it's STM32F0 51RAT6. Let's go back to our development environment and check this. Yep, it's the same processor. So click on this and hit Finish. And then it brings you to this new page, which is called the repository. So one kind of fancy feature of this IDE is that it has all these pre-written libraries that you could potentially enable. For example, if I wanted SPY to be in my project and I wanted SPY headers and source files to use, or pre-written drivers, all I have to do is click this checkbox, and voila, they appear in my development environment. So that's kind of fancy. However, I'm the type of person that likes to write pretty much everything from scratch. So I'm just going to use the core defines for the processor, which is this CMSys boot and M0 CMSys core. So I'm just going to have these two checked, and that's pretty much just all I need to do on this repository page. Next, I'm going to go into my main, and there's my main function. And this video assumes you know the basics of C and have at least worked with one processor or more in the past. So hopefully you know what a main C function is, for example. If not, regrettably, this video isn't for you. But our goal is to blink an LED on our specific processor. So the first step in our main file is to include the defines for that processor. So I'm going to do a pound include, I believe it's this file, STM32F0 xx.h. And then I'm going to hit the hotkey F7 to do a build of the project. And you'll notice I'll get some errors. Now these errors are quite unfortunate. I don't know if it's a bug in the IDE or where these errors came from, but essentially you got this startup file here. And if you take a look at the startup file, these are all assembly commands. So this is actually an assembly file. However, in our case, it's listed as a .c file. So we need to right-click on it, go to Properties. In the Resource tab, hit Edit, go to File. You're going to have to locate it in your workspace. So I believe it was Blinking LEDs 2, CMSys boot, startup, and here's this .c file that actually needs to be renamed to a .s or assembly file. And you're going to want to load that file in, hit OK a few times, hit F7 to rebuild your project, and voila, your project rebuilds and you don't have any errors. So from here we're good to go and ready to start attempting to blink our LED. So let's reference the schematic again. There appears to be not too many features on this board. However, I'm not going to complain given the price. Appears to have two LEDs and a push button, as well as, of course, some breakout headers, I'm sure. So we got a blue LED, a green LED. They're connected to PC9 and PC8. If we copy and search for that, we see that it's directly connected to our microcontrollers. So we're directly driving these LEDs, and so a 1 is going to be an LED. A 1 on the digital output is going to correlate to an LED that is on, and a 0 is going to correlate to an LED that is off. And it's connected to this net called PC8, which is connected to a pin, I believe 39, which is called PC8, provided we want to blink the blue LED. And PC8, what I assume that stands for is port C. Some microcontrollers enumerate through their ports numerically, such as port 1, port 2, port 3, port 4, etc. of GPIO banks or general purpose input-output banks. In this case, they're doing it alphabetically like PIC processors, so you have port A, port B, port C, etc. And so basically what we want to do is we want to provide a clock to this port. We want to tell this GPIO port that it should act as a digital output, and then we're going to want to be able to assert that output high and low, high and low, high and low, so we can blink our LED. Now in order to do that, you're going to need this document of regarding this processor. Usually you have two core documents that a manufacturer provides. You have a datasheet which contains hardware parameters, and then you have a user manual or reference manual. In this case, I believe this lovely 748-page document is called a reference manual. Anyhow, this is basically your programmer's guide to the microcontroller if you're attempting to write your own libraries as opposed to use what someone else already wrote. I like doing things from scratch when I can, so I'm going to attempt to use this manual in order to blink an LED. And now, ARM processors have some advanced features, such as you can turn off clocks to certain peripherals in order to save power. However, we want to enable those clocks. So there's this reset and clock control register. And then one of these registers on here contains information about applying a clock to our port C peripheral. So let me just scroll through here and try to find it. AHB, I don't know what that stands for off the top of my head. Peripheral Clock Enable Register. If we scroll down to the bit descriptions, there's this, let's see, bit 19 in the register, which correlates to the I/O port C clock enable. So we're going to want to write a 1 to this register. In order to do this, generally I just copy and search for the register within the integrated development environment and within the core processor define file, which is this STM32F0 xx.h. So this is a little technical, and you can use the pre-written libraries, and that wouldn't require going to these links in order to blink an LED, but I enjoy doing it nonetheless. So this AHB enable register that I got from the user manual is part of a C structure called RCC. So in order to access it, I have to type RCC member, and if I hit Control Space, whoops, I can't do it twice, but if I hit Control Space, I can bring up the members of that C structure, and I believe the user manual said it was the AHB enable register, and I believe it was bit 19 that I wish to write a 1 to. So I'm going to write the pipe equals, which is the bitwise or compound assignment operator. And then I'm going to want to shift 1 over 19 times to write a 1 to that 19th bit in that register and nothing else. That's what this compound bitwise assignment operator does. If you don't know what that does already, I recommend you study up on your C, and if you Google it or Wikipedia it, you should find plenty of useful and helpful information regarding that. Now, to spare you subsequent user manual lookups, the next thing I want to do is I want to tell that GPIO pin that it should act as a GPIO output. So let me add some comments here. This was to enable clock for port C. My next step is to enable port C pin 8 as a digital output. So again, I've already done this before. I know there's a C structure that is called GPIO-C, and there's a member of that structure, if I could type right today, GPIO-C member, I believe it's called mode register, and we want to set our 8th pin as a digital output. So to do that, I have to write a 1 to bit 16. Now, I doubt you're going to understand that just by looking at it. Again, I'd recommend using the user manual as reference as I'm doing all these various steps on the screen for you. I'm just trying to make sure that this doesn't end up being a video that's over an hour long. So anyhow, so now I've enabled that pin as a GPIO output. The next step is to turn GPIO C pin 8 on or assert high. So to do that, I write to a register GPIO C output data register, I believe, and it is the 8th pin on the port, so it is simply the 8th bit in this register. So if all goes well at this point, I should be able to turn on the LED. So I'm going to hit F7 to compile, and then provided you did all this setup correctly in order to get your ST-Link to work, when you hit this debug button, you shouldn't get any errors, and you should actually be able to flash to your processor. So let's wait a little bit for that to flash. And then up here in our debug options, we hit play. And then if I take a look at my board, the blue LED is now currently on. And then another fancy feature about having live debugging, I already assume you are aware of this. However, in the unfortunate event that you are not, the nice thing about this is you can actually go through your code line by line. So if you notice, the LED isn't currently on. However, I can step through my code. I can step through line by line, and you'll see as soon as I execute this line here telling our GPIO to assert itself to a logical high, which in our case is 3.3 volts, which is our supply voltage, we will see that the LED should hopefully turn on the webcam. So I step over, and aha, the LED is now currently on. So pretty simple. Now the next goal is, of course, to blink the LED. So in order to do that, I need to turn the LED on for some duration of time, then I need to turn the LED off for some duration of time. So in order to do that, I need to actually delay. So the easiest method to delay is to have some for loop delay. So I'm going to define a volatile unsigned int I equal to 0. And this is a variable that I'll just be able to enumerate through for my for loop. And then, so in my while loop here, basically that's an infinite loop. While 1 is equal to 1, keep looping. And, well, basically that's forever. So for I equals 0, I less than, we'll do 1,000,000. Hopefully that's enough delay. Increment I. And so basically what this is we're just wasting CPU cycles. This isn't the ideal method to implement a delay, but it works for this video. So we're going to want to delay, and then we're going to want to turn our LED on. We're going to want to delay again, and then we're going to want to turn our LED off. So again, this pipe equals is the compound bitwise assignment operator, and we can use it in this method to write a 1 to a specific location in a register without affecting the other bits in that register. However, in order to turn the LED off, we're going to have to write a 0 to that specific bit without affecting the other bits. So to do that, we use ampersand equals tilde. This is bitwise and compound assignment operator. The tilde is the bitwise not, and I'd suggest working through this yourself on paper to see exactly what's happening, but this essentially should work here for blinking the LED. First we delay, we turn the LED on, we wait for some time, we turn the LED off, we go back around in our loop, and we wait some time. So I'm going to hit F7 to compile. That doesn't appear to be working. That's because I'm still in debug mode. Now that I'm out of it, I'm going to hit F7 again, and our program compiles. I'm going to flash it to our processor. And hopefully, with any luck, once we run this program, our LED should be blinking. So I'm going to hit play. I'm going to look at my webcam quick. And it appears the blue LED is blinking. You'll notice some other LEDs are blinking in the background. That's just informing us that our USB link is active. So anyhow, I know this tutorial could have been a little bit more in depth, but hopefully this empowers the majority of the people watching this to be able to easily get into this ST development board, because it's a really underrated board. Some other boards are a lot more popular, but they're definitely not as fast or as powerful. So as soon as you can start learning how it works, hopefully the better environment that we can get out there for the users of this development board. So anyhow, I'll be using this for some future projects, and I might be making a few more videos if anyone's interested. Hope this helps, and yeah, we'll talk to you later.